All right, so let's ignore the day cycle for right now. And let's just go into the update loop. And let's get this clock working as intended from the web tutorial. And then I'm going to do my modifications of it for us. Cool. So I'm going to take out this return statement so that the update method can run. And here we were grabbing time discrete. So this date time object. And here we're going to go and check out, if you go into date time, if you go into its now property, which is like, give me the date time struct of right now. And then we go into the time of day property of that. We'll just get the time span. So it's not going to cover the date. It's just going to give us details on the time of day. And we're going to put that into our time continuous variable. And remember, this update loop is running every frame. Oh, actually, you know what? Before, let me just talk about the issue with the discrete time. So the problem is it's not really like half an hour past. But if we see here, it's 3:07, and if you notice in the hours arm, it's like dead on 3 o'clock. And that's because we're pulling into the integers, we're pulling into discrete time. So just the whole number of the hour, the whole number of the minute. So let me just move the minutes arm a little bit. Be like, well, what if it was 3:30, right? Well, this hour hand is like inaccurate on how we're used to reading the clock. This would look strange to us because if it's 3:30, it's 3:30. So the hour hand would be rotated halfway between 3 and 4. We're moving from 3 to 4. So we have an additional rotation that we have to consider. So just getting the whole hours and minutes doesn't give us the full story. But you know, we could take the minutes and do a calculation like how much additional of an hour that is, a fraction of a unit. But we also have time. We also have this time span object, which gives us some more of a continuous variable. Gives us like a fraction, the fraction of an hour, the fraction of a minute, of a second. So this is interesting to look at. So we're going to update our hours and our minutes rotation based on that. So everything looks the same. We're doing quaternion.euler, and x and z are 0. And then this is a little different. Here we're going to go into time continuous dot total hours, which if you see is a double. So doubles are decimals. They have a decimal part, and they're similar to floats. But a float is half as precise as a double, and hence the name double. Basically, it's a double is double the memory of a float or a single precision. And it's double as precise, but it costs double as much memory. So you get like a really long decimal number. Now, usually you don't need that type of accuracy. Usually that accuracy is only really warranted for scientific or financial software. So actually Unity doesn't even support doubles because floats are half as expensive memory-wise, and they are precise enough to do, you know, the physics and all this type of calculations and stuff we're doing. So notice this is returning a type double, but a double isn't supported in Unity, so you have to cast it down to a float. So when you do these parentheses and you put a type in it in front of another variable name, it's going to try to cast it down. It's going to try to convert it. I shouldn't say down. It's going to cast. It's going to convert it. So in this case, we're casting down, going from a double to a float. We're just losing some precision, but we don't really need it. We can also go down from like a float to an int. We can like cut off the decimal number, and we only want to use the integer. And usually you go down, you want to remove some precision or some part of it. You can cast up. You can go from like an int to a float. but you're not going to gain any extra information. Like if an integer was a 2 and you casted it to a float, it's just going to become 2.0 because there's no, like, it's not some magical new information will appear in the decimal part. And you can go from a float to a double, but again, there'll be, in that extra precision, there's nothing there. It'll just be zeros. So, and you can cast from like an int to a string, and I think it would give you the string representation of the integer, or it might look up like the ASCII code of like this number. Like each character in a string is actually represented by an ASCII code, and either that int is just cast directly as a string representation, or it might try to look up the ASCII code that number represents. But anyway, here we are casting down from a double to a float. We're casting from a double to a float so that we can use it still. So now we have, like, instead of a 3, an int will be like 3.2. You know, it's like we have some passing of 3 p.m. Well, it'll be like 15. It's p.m. So it'll be like 15.2 or whatever. And same for minutes. And so now we can get that like fraction of a movement, which we're more used to with clocks. And for right now, I'm going to leave it on real time. Not real time, sorry, continuous. Forget real time. I'm going to cover this later. But if it's continuous, do this, else do that. And notice if it's continuous, we're going to just do a similar thing. We're going to get total seconds, multiply it by degrees by second, but we're going to cast it to a float. So let me just show you continuous first, because I think this is what you might be used to with your clock. So though I've seen clocks operate both ways. Notice everything went dark just because we're animating the light source as well. And I was messing around with this in the other class. And 3 p.m. wouldn't be this dark. So hold on a second. I'm supposed to do that. That's fine. This will get updated. All right, so if I click play, this is what the light will look like at 3 p.m. So here we have the hour hand is just a little bit past 3 o'clock, which would be 90, because we're at like 3:13. And notice that it's rotating, updating ever so slightly. And if I go to the minutes, notice we're at 3:13, so this is the number of rotation. And notice it's moving a little bit quicker because we're moving past a minute much quicker than we move past an hour. And if I click on the seconds arm, you can really see the rotation moving, and you can really see it here, like it's moving a full rotation every minute. And if you really watch the minute hand, you can ever so slightly see it moving. But you can see these are being updated in our update loop. They're being run in real time. And if I turn off continuous, notice that the clock hand now jumps. It jumps every second. So I don't know if I'm dating myself, but I don't know if you've seen analog clocks that have moved in either way. But here we have a discrete motion on the second hand, and only when we move from a whole, from like a 3 to 4 to 5 to 6 seconds will the rotation number change. And notice we have nice clean rotation numbers because we're only receiving an integer of the second. We're not receiving the fractional part of it. So the rotation doesn't change for like that whole second. That's like a 3 or 4 or 5. It stays at the same rotation, and only throughout each of those update frames for that second. And only when that second moves to the next integer will that second hand pop. And if I go back into clock and turn it back to continuous, notice the movement is now looking like it's like fluid. It's giving the idea of real motion, and we can see that the rotation is updating in more of these like fractional units. And even though it looks fluid, it's just that the update frames, the update loop is called like 30 times or 60 times a second. So it tricks your eye into looking fluid, but it actually, in a really, really, if you were like do like a slow camera or speed or something, you would see that there is little, it's not like fully continuous. Anyway, it is good enough. The update loops are fast enough that it tricks our eyes. So what was happening with, okay, if this is true, we do that, else do this. So that was me toggling that on and off in the inspector. And here we notice that we're still just updating seconds transfer and the local rotation of it. The only thing that's changing is, are we grabbing time continuous dot total seconds, which is a double, and we're casting it as a float, so that we have a fraction of a second, or are we grabbing time discrete dot second, which is an integer, so that even though this is updating like 30, 60 times a second, you only really see it updating once a second. All right, so that's update discrete and update continuous. Now let's tackle this idea of animating the sun. So if I go into my direction light, if I just pull it out of the parent group, because I have to explain why I parented it. But notice it's the icon is pointing straight down. This is driving our like sun system. If I look up, it's like high noon. The sun is directly above us, and that's what the little icon of the sun looks like. And if I rotate it, notice that I've rotated the sun down into the horizon. So when the sun is at this location, either it's like the beginning of the day or the end of the day. So it could either be like 6 a.m. or 6 p.m. Just depends how you figure out your rotations. That if I rotate it all the way over here, again, it's at like a dusk point. This could be either beginning or end of the day. And then if I keep rotating it to where it's like completely underneath us, this would be like midnight. The sun is like on the other side of the planet. So even though we rotate the sun in our little artificial simulation, you know that it's really the sun, how we're rotating around the sun, but it feels like in our situation that the sun is rotating around us, which is why you can change the sun position like this. Now, for me to get ready to animate the sun, I have to think about, okay, at noon, on our clock, it's like a rotation 0. And when the sun is down, getting low, like that should be like a 6 p.m. So like when the sun is setting, or if we're going at high noon, so noon and then 6 p.m. So that should be like 180 degrees. That should be the bottom of our clock. And then as the sun comes up to midnight, the sun returns back to its upward position, like 360 or 0. And as we come back to like 6 a.m., it's really, we're pointing down here again. That's really like a 180. So I need to somehow figure out, okay, this clock at high noon, I would really like it to be at 0. So it's simple math for me. But if you notice that I have it's rotating around the X. Okay, I figured that out. But it's like 90 degrees off. So I'm going to use parenting, but in like an opposite manner than we were using to build the clock and to animate the clock hands. I'm going to make an empty game object. Let's call it daylight. And notice I rotated it -90. And everything else is just default. And so it's almost opposite of what our light source is when it's set up at noon. And so I'm going to drag it in. And when I do that, it's going to inherit the transform of its parent. So notice it was at, when it was at 90, now it's at 180. And, that's my fault. I think I was messing around with these. So let me see. 0. Oh, I think that's correct. Let me see how I'm using, because oh, right, because we're doing, so a clock moves 12 hours in a day. So that's why we did 360 divided by 12 to see what a full cycle is. But a clock has to rotate twice throughout the day, whereas the light source, Earth, is going to rotate around the sun once a day. So it's 360 divided by 24, right, or 15 degrees per hour, which is why up in my constants now I have this degrees per day cycle of 15. And if I zero this out, I'm at midnight, so that's good. And if I move 90 degrees, I'm at 6 a.m. And if I move 180 degrees, I'm at noon. And I move another 90 degrees, 270, I'm at 6 p.m. Okay, and then I move 90 again, I'm back at midnight. So I did this offset. I put it in this parent, and I did this offset based on just the nature of the sun system. Just had that kind of 90 degrees thing. So I'm using parenting to offset that, so I could do simple math to animate the light source. So first off, we need to get we're going to get the transform of the day cycle. So we're grabbing the actual directional light, not the parent. We're actually animating the child, which is opposite how we handle the hours, minutes, and seconds. And on awake here, we're going to say, okay, what are we setting the local rotation? We're going to ignore the parent rotation, make it easy math. And we're going to do the Euler static method call. We're going to get the number of hours that are currently happening and get the hours there, get the integer multiplied by degrees per day cycle, which is 15. So right now we're at 3 p.m. Or 15 hours. And so 15 hours times 15 degrees, and we've moved across the sky. If I go into my scene view and look up, we've passed noon, and we've moved a few hours past. We're now at 3 p.m., right? So how do I test this to see if this is working all right? So I have it in my awake, my initialization, and then notice here, if real time, we just update our day cycle as normal. But if it's not real time, this is where I could do my testing. I'm going to take my day cycle and I'll multiply hours times degree per cycle. Now, hours gets updated initially by the number of hours in a day, but what the real use of it is it's public, or it's a serialized field, so I can mess around with it, and it's an integer, and it ranges from 0 to 23. It goes the entire day, right? So if I go into the clock and I turn, okay, real time happens to be off, so that's awesome. So I'm going to zoom out a little bit, and I can actually, after awake, after initialization, I'm actually allowed to adjust the hour of the day. It's not messing with the clock, it's just messing with the daylight cycle, just to make sure, wait, am I doing this right? Because I had to figure out that math. So if I go to 0, we're at midnight. That looks right. If I go to hour 12, the sun is directly above us. That's correct. So if I go to hour 6 a.m., the sun's on the horizon. It's just behind the clock. So that's right. And then if I go up to 15, 3 p.m., the sun is coming down from the top, and we're starting to get sunset around 18. And so that looks right. So I'm testing it, and I could turn it back on to real time where it should be, which is up here. So that was the point of having this real, are we in real time or not? Are we allowed to change it, and exposing out the hours like this, which allows me to do my testing here with the sunlight to see if I've set up my math correctly. And notice we're animating on X, not Y or Z. All right. Yeah, and I went over continuous and discrete. And so now we basically built the clock a little bit further beyond the tutorial here. So after class, I'm going to ask you to go through his entire tutorial, the second half of it, and write the script the way I did. Understand what's happening. And I'm going to turn this script off, and I'm going to jump over to this script here. And this is going to, this started with the same origins of this, but I did a few more features that I want to cover. So I just put like a return statement in here just to like turn that script off because I have two scripts on one object. So the top is the same. I don't have that like real-time testing, so I don't need it anymore. The big addition here is I'm going to put a little button in front of the clock. And just gotta let my scripts recompile. And notice now we have this AM PM button. So if I click play, we're going to jump between 3 p.m. and 3 a.m., which would have no light. Notice I'm clicking on the button and it's updating the daylight. So what I have here is in my UI canvas, I've got this button AM PM. It's just a basic UI button, which I brought down from here. And I just positioned it in the top corner up here and just pinned it in the top left corner. And just notice that I positioned the clock just a little bit behind my UI. So it's sitting up here, way up here. It's part of the UI. It's just a little bit behind so that the button sits in front of it. And this button is a normal button. And when you click on it, it says, well, what am I going to click on? Well, like when this event gets fired off, who's listening to that event? And I have a public method in this clock script. I'm going to cover this next week, but it called update AM PM. So notice here, it's this clock object, game object, go to the clock script on it, and call this update AM PM. So that's the public method of my script that the UI event will call. And what's happening here? So I'm listening to the UI this way, but I'm also updating the text on it. So when I click, based on the time of day, it checks is it AM or PM. All right, so that's why in clock script here it says this text element. So it's like, okay, what is this text element you want me to update on the UI? And I need to keep track of, are we in AM or PM or not? And so this text element is just right here underneath the button. I have a little text element, AM or PM. You just update it. So if we go down into the awake, the initialization, here we just do our check. If hours is less than 12, because we're running on a 24-hour clock, we know that we're in AM. So is AM becomes true, and we go out and we update that text element to AM. Else we know we're in PM, so this becomes false, so we update PM. And this don't worry about this for right now. I'm gonna have to cover clicking on like the little hour indicators. It's gonna take some time to cover, and I'm gonna run out of time. So I'm just gonna cover this, and then we're done. So this is a public method that clicking the button executes. So if we're in the AM, I'm going to first set that bool to false because we're going to move to PM. And I'm going to update the text on that UI element to PM. And I'm going to add 12 because we're in a 24-hour clock. So if we're in AM, so if it's 3 AM, add 12, we're at 15, which is 3 PM. Else, we must already be in PM, so we're going to move to AM. So this becomes true. We're going to update our text to AM, and we're going to subtract 12 from our clock. So if it's 3 p.m., it's hour 15, take away 12, and we're at 3. And so this, once we update those hours, we go, that next frame, we go into the update loop, and we hit the day cycle here, and notice it's reading in hours. So it's updating the number of degrees of rotation of the daylight child game object. And so it changes the sunlight in the sky and stays updated afterward because this hours property is updated. And notice that we're also updating our hours transform, but when you go from 3 a.m. to 3 p.m. on a clock, since it's a 12-hour clock, it looks the same. All right, and so next week, what we need to cover is how do we click on these little hour indicators that have a collider on them, and we could read in their rotation. So to understand if we're clicking on them, we're going to have to go back into the click detector script, and we're going to have to use our user input check, and then we're going to have to call onto the clock script, which is what this update time is for. And so this is going to take a while to explain, and I got to cover the colliders, and I got to cover this physics layers and how that's working. And then next week is the last week of week 3. So I should really cover the glow slider, the opacity slider, this time slider, time to destroy slider, and the fact that our paint strokes are very dynamic. They're squishy or they're elongated based on how quickly I'm moving the mouse stroke. And notice that, we've got like glowy semi-transparent objects now. So I got to cover how glow works, opacity works, and different types of time destroy amount, and how to make these painted strokes, like read in how quick your mouse speed is. And then that'll be next week. And also how to change the time of the day. And that'll be everything for the Section 3 quiz.